that we've discussed dynamic RAM and with that finished our two popular volatile memories, SRAM and DRAM, we can go on and move to non-volatile memories. So I want to discuss memory volatility. SRAM and DRAM are examples of what we call volatile memories. That means that they only store their data as long as the power source is connected. Mask ROM and OTP are non-volatile. Their content is saved regardless of the state of the battery. But what about non-volatile read-write memories? Well, I'm going to introduce something called the floating gate transistor. It's also known as EEPROM. So we can see here the schematic symbol on the left-hand side here of an NMOS, but it has an additional line there in the middle. And that's because this is a floating gate. What we have over here is just a standard transistor, as you can see, with a source and a drain and two N+ regions. But instead of just having an oxide and a gate, we have an additional floating gate inside, another piece of polysilicon over here that is shoved in between two pieces of oxide. So that is our floating gate. And I want to proudly show here that Gordon Moore mentioned about this EEPROM, that as important in the development of the microcomputer industry as the microprocessor itself, discussing the invention of the EEPROM, which was invented by this guy over here on the bottom right, whose name is Dov Froman. And he is an Israeli, just like me, and actually we can thank him for bringing Intel to Israel and starting the Israeli high-tech industry as we know it today. So why does a floating gate work? How is it a non-volatile read-write memory? So let's see how we program it. So it works using avalanche injection. We take the source and we ground it. We take the drain and we connect it to a real high voltage, something like 20 volts. And then we take the top gate, the gate that we do have connected to a terminal, and connect it to something very high, like 20 volts as well. So what this is going to do is going to turn on the transistor. It's going to cause a lot of current running through the source and the drain with a high field on it. And what's going to happen now is that it's going to pull a lot of these electrons that are going to jump over the potential barrier over here, the oxide, and they're going to get stuck on the gate that's in the middle here. Okay, they're going to keep on getting stuck there actually until we basically change the threshold voltage of this. The trapped charge is going to reduce the vertical field that's going to be applied here on the channel below, and so it's kind of a self-limiting type of a process that's going to stop until we finally get a certain amount of charge over there. So in the end we have this higher threshold voltage over here, and when we put a voltage that is not so high, such as 5 volts, I mean that nowadays would be high, but in those days that was a standard voltage, then it's not going to be, then we've changed the threshold voltage. We can look at that in this type of a graph, which this is just like a VT star type of a model of a graph. So here we have VGS to IDS, so usually we see this, in our way, something like that, but if we looked at a VT star model, we assumed that things would turn on, at VT star. So these are the VTs that we get from the 0 state and the 1 state. So programming our transistor, we would move our state between these two graphs of our VGS to IDS. And if we put on our operating voltage, such as a 5 volts right in the middle, if we're in the 0 state, we're going to turn on that transistor. If we're in the 1 state, the transistor is going to stay off. Our VDD, our operating voltage, is lower than VT in the 1 state, and so despite putting our VDD on the transistor, we're still going to be off. So that is how these types of a floating gate type of a structure works. We program the threshold voltage of our transistor. We change it by moving charge onto and off of the floating gate. So the problem with the floating gate transistor that we saw before, the EEPROM, is that it is electrically programmable. If we want to erase it and we want to return it to the state where the charge is off it, we have to take this this device, or the whole circuit, and stick it into an ultraviolet light, which will push out the charge from over here back into the substrate. So that is how we erase such an EEPROM. And so it's an electronically programmable transistor, but it is not erasable. We had to do that externally. And the next invention is the EEPROM, which is the electronically erasable and programmable read-only memory. So in this case, we take the same type of a structure, so we have the floating gate, but there's this like a reduction on the side here of the floating gate, which makes a really close, thin oxide that overlaps the drain part of the transistor. And that actually enables us to apply Fowler-Nordheim tunneling and to tunnel the, to move the charge that we got stuck on here off of that. So what we can do now is we can program it regularly the way we did before with this avalanche type of a programming. So we put a high current running through the channel that has a high electrical field on it, and we put a vertical field that is applied to the same charge and make that charge jump over the barrier and get stuck in here. So that's the same in that case as the EEPROM. But then when we want to erase it, what we're going to do is we're going to put a field that's going to pull the charge out through the drain over here using this Fowler-Nordheim characteristic. Okay, so this is the EEPROM cell. The problem with it is that the absolute threshold control is really hard. The unprogrammed transistor might be depletion, so when we erase it, we might really take the VT so low that it will be depleted, that it will be always on. And therefore, what we had to do with the EEPROM cell is actually add another transistor, a select transistor. So as you can see here, this is the EEPROM cell, okay, with this little thing here for the Fowler-Nordheim tunneling in its symbol. And we add to it another select transistor. So this will always get VDD. And when we're programmed and the threshold voltage is high, this will still be off. When we're erased and the threshold voltage is low, then this will always be on. And then, therefore, just by opening or closing the word line over here, which is with a regular transistor, will either cause current to flow or not allow current to flow, depending on the state of this, if it's a 1 or a 0. So what we have to do is we have to program it such that VT is higher than VDD, so we have to pull charge onto the floating gate just enough so that VT is higher than VDD, and then even this application of VDD will not turn on this transistor. And then we erase it, we make it really low. We make it so low that it could even be always on. It could be that VT is smaller than 0. We don't really care as long as it's always on. So that's how the EEPROM cell was built. The true innovation that made this become something that we all have, in our pocket and everywhere was the invention of Flash. And Flash is just basically the same thing as EEPROM was. So we have here, just the regular floating gate with a thin tunneling oxide and so forth. The big deal about Flash is, and the thing that made it really stand out, is the way that it is operated. So the guys who invented Flash understood that the problem with erasure that makes us put this additional transistor in the mix can be alleviated if we go and we do a controlled type of erasure. So if we erase and then check what the VT is every once in a while, then we can easily use it as just a single transistor and not have that select transistor along with it. The problem with that is it's a long process that isn't worth doing. But if we go and take a whole large block of Flash of the EEPROM and erase it all together, then we can just do that every once in a while, and it'll take a long time, but that's okay. So what we do with Flash basically is use that same type of EEPROM cell, but we do a controlled erase on a large block of data. We can therefore program a single bit, but to erase, we have to erase a whole block. And that's how Flash works in our computers and so forth. We work on blocks when we erase them, and then we bring them to their initial state, and then we can go and program bit by bit. So just looking at a cross-section of this, a regular EEPROM, as we can see here, is with the floating gate over here, but it doesn't have this thin oxide. And on the other hand, we have the Flash cell or the EEPROM cell, where we have this overlap of the source and drain with the thin oxide that allows us to So there are two major architectures of Flash which are resemble what we discussed before on the read-only memories, and they are called NOR and NAND. So NOR Flash, as we can see here, it has a word line the word line is connected to a transistor, to a floating gate transistor, and we have a bit line over here that is contacted to the floating gate transistor, and then we have ground, that goes underneath. And what we see here is that the layout of this is 5 feature lengths by 2 feature lengths, so it's about a 10F squared type of a cell, because it needs this contact inside each cell, as we saw beforehand when we discussed the layout of a ROM. So what we have here is a NOR structure, because we only need one cell to discharge the bit line to ground. Okay, so we get a real fast read, but it needs a contact inside each cell, and that contact costs us in terms of layout. On the other hand, we have the NAND type of cell, where we have our bit line. We only have one contact over here that goes into one cell, which is connected to a word line. That is diffusion connected to the next cell, the next floating gate transistor, which is connected to a word line, and so forth and so on. And that really saves us the need for an additional contact. And we only have one bottom row over here, which we call the source line. And so that enables us to do a real cross-point layout, where we just put the floating gate transistor underneath one word line and the diffusion over here, and we can get a minimum size cell, which is 2 feature sizes by 2 feature sizes, as I'll show you a bit later. So we get a 4F squared cell, which is a lot smaller than the 10F square of the NOR flash. And that's why, despite having a much slower read, because we have to actually go through a long stack of transistors, a serial stack of transistors to read out the data, it still makes it so much more dense that NAND flash has really overtaken NOR flash as the flash that we use in everything, from SSDs to disk on keys to flash disks and so forth. They all basically use NAND flash. NOR flash, on the other hand, is used in things like boot ROMs and so forth, where they're really read-only memories. We only flash them, we only program them once in a while, because programming takes a long time for NOR flash, much longer than for NAND flash, but we don't need usually as much density, and we'd rather supply it with faster reads. So let's look a bit at the operation of these guys. So with NOR flash, how are we gonna program it? We're going to again apply this vertical field. So we put a high voltage, something like 6 volts on the source drain, on the VDS, and we put a really high voltage, something like 12 volts on the floating gate. So we're going to select this cell. We're going to put 6 volts running on the bit line over here, and we're going to put 12 volts on the cell that we want to program, and this will cause charge to jump onto this floating gate and program it. Okay, so we're going to run current through and apply a vertical field, and it takes a long time. It takes microseconds to program one of these gates. Okay, then we're going to read out and see that the programming was successful, and if not, we're going to repeat repeat it until we get a successful read. To erase, on the other hand, what we're going to do is we're going to first go and program all the cells in the block. So we're going to just go and bring them all to a state where they have this high voltage. Now remember that the threshold voltage is self-limited. So we're going to be pulling charge onto here, but the charge that's going to be here is going to reduce the actual electric field that is going to be applied across the bottom gate oxide over here. And so it's going to actually be self-limited. The more charge that jumps onto the floating gate, that's going to limit the field over here, and then less charge will be pulled. So first of all, we can go and we can program the whole thing. So we bring everybody to be, all the cells to be pretty much a similar VT. And then we go and erase the entire block. And the entire block is the thing that is hard to know how, if we erased it enough or whatever. So this is going to be a longer process that's going to be iterative, and we're going to do it at the whole block at the same time. But since we programmed everything to the same level initially, it's going to be, easier to erase it without too many iterations of verification. Finally, how do we do read? We put a regular, kind of voltage across the source and drain, and we read it with some sort of a word line voltage that's going to be between the 2 thresholds that we saw before. If we saw that there was these 2 thresholds, we're going to use the read is going to be somewhere over here. This is going to be the V read over here. Okay, so we apply a median voltage on the gate, something like 5 volts. A 0 state, the bit line will discharge. The 1 state, the bit line will stay charged. So that is how we read the NOR flash. NAND Flash is very different actually. In NAND Flash we have a much more complicated type of an operation. So what we're going to do to erase is we're going to take the source line over here and we're going to put 20 volts, real high voltage on the source line, and on the bit line we're also going to put a high voltage, so we're going to have 20 volts over here. On the word line we're going to have a 0, and what that is going to do, it's going to actually put, on the source to gate is going to have a very high negative voltage, and it's going to pull all the charge that we put on the floating gates over here, it's going to pull it off of them through that Fowler-Nordheim tunneling. To program, what we're going to do is we're going to disconnect the source line, we're going to drive the bit line now to 0, and we're going to put something like 20 volts on the word line. So now for the selected word line we're going to put a high voltage, which is going to pull charge onto it. For the unselected word lines we're going to put a standard voltage, something like 5 volts, which is going to make sure that these guys are on and allow the voltage of the bit line voltage to cross through between them. Okay, so that's how we're going to program it and write a 1. So everything's going to start off as a 0, and then we're going to write 1s on only the bits that we decide to select with the word lines with the high voltage. For read lines, we connect the source line, we connect the bit line, and then for the selected we put a 0 volt, and for the unselected we put 5 volts, and therefore we read out that certain cell. So that is NAND Flash. So it's a bit differently operated. When we look at NAND versus NOR architectures are large but fast. In fact, NOR is actually really fast for reads but slow for writes and erases, because they need this precise control over the threshold voltages, which are harder to So NORs are used for applications such as program code storage that are read a lot and at high speeds. In other words, your types of boot ROMs and so forth, they'll be NOR flashes. But really NOR flash is kind of a niche application nowadays. It's made by very few companies and in usually small sizes. There are different plans and attempts to make to reinvent NOR flash and give it higher density and so forth, so it'll be used more often. But at the current state, it's really a niche application. It still has a lot of sales, of course, but it's not something that's being developed very aggressively like it was in the past. NAND flash, on the other hand, they're slow, but they're very, very, very small. In fact, just reads are slow. Programming erasure are okay speeds. Okay, and so they're used for video and audio file storage wherever we need high density. They also use faster write and erase times. So they're really a much better solution than NOR for most things except for these high-speed reads. So anything that we really need read and write ability and not just read, we're going to be using NAND, and especially if we need high density. And NAND it's really a lot smaller. It's like 40% smaller than NOR in its initial state, and we'll see that in fact it gets even smaller than that. So it generally uses Fowler-Nordheim tunneling for both program and erase. So how can we increase flash density? How has it gotten to the state where it's so much more dense than NOR flash that we actually hardly ever use NOR flash today, except for in these boot ROMs and so forth? Well, the first thing is that we can add levels to every bit, and this is a multi-level cell. Actually, the first one was invented by an Israeli company called Saifan, where they were able to put several levels inside a bit. But nowadays you have really, the standard thing would be a single level cell where we can store a 0 or a 1 inside a cell. A multi-level cell will have 2 bits per cell, that means 4 levels. A triple level cell, which will have 3 bits, in other words 8 levels in a cell, and we even have quad level cells. So if you can get one single transistor that can hold 16 levels, that increases our density by 16, and that is something that exists today. The other way of doing it is actually going in the third direction. So this is a planar NAND architecture where we just have, similar to our CMOS technologies and so forth that we've learned, we just have one level of cells, and that limits the scalability and the density because we're only going on one plane. But since everything is so really regular and so forth, and flash is connected, source to drain, and so forth, what they've actually done is they've been able to build these long stacks of the transistors, and we have the third dimension of the NAND flash already a long time ago. So 3D NAND has been, has been developed very well, and every year or two they're adding more and more layers, and we currently have at least 128 layers. They're going for even higher than that. You can look at the news today and see what the latest thing that Western Digital or other companies have announced that they are able to do in terms of NAND layers and in terms of how many levels they're able to put in the cell. I do want to mention here that these things are very unreliable. So the fact that we do these aggressive types of things, especially this multi-level cell type of operation, it means that a lot of bits come out really bad. Number one. Number two, since we're doing this type of tunneling through the oxides, we're breaking things down. And there is a limited endurance of these types of structures. So they break down after a while. We have a limited number of writes that we can actually apply to such a cell. And therefore there is a lot of information theory that goes into how we can really distribute the writes over the different areas of the SSD or the flash arrays, number one, and number two, of how we can really get rid of the bad cells and fix errors. So we don't actually get the number of bits that we fabricated, but we're still able to get it in such a way that this extreme increase in density that has been able to get gives us a huge density. We have SSDs of terabyte and more than that nowadays in what used to be when flash first came out, a number of kilobytes. So using these great ways of doing different flash controllers, we're able to get this high density for flash, for NAND flash, and even though the next thing we're going to discuss, which are the emerging memories, have threatened to kill off flash for many years, flash continues to grow and scale, and is still thriving today, and is expected to thrive in the years to come, despite the fact that the technology is something that is relatively been around a long time. It's a veteran technology, and there are the new guys who are waiting around the corner to kick it out haven't succeeded yet. So with that, we're going to finish talking about the standard non-volatile memories and go to the things that are up and coming, the emerging memories.